Hi guys, happy Monday. Hope everybody had a very good weekend. Just to give you an update, everything went well with the baby. We're happy and healthy, and mama and baby are doing well at home. I'll probably be back in on Thursday, guys, so you can stop freaking out and we'll resume as normal on Thursday. So, today, you hopefully should have gotten a tan sheet on your way in, and we're just going to walk through it like we kind of did on last week, Thursday's class. So, let's start with number 40 from chapter 13. Today is all about Kp, which again is an equilibrium constant using pressures. Pretty simple, straightforward, products over reactants. And yeah, let's just give these a shot. So if we look at number 40 here, we're asked to find whether or not these conditions are at equilibrium. So the very first thing we should do in this problem is we should set up a Kp. And why don't you go ahead and try that right now. You can pause the video. Okay, you should have gotten a Kp that looks like this. All right. I kind of misspoke. I apologize. It should be a Qp because we're not quite certain whether or not these conditions are at equilibrium or not. So if you're not sure, it should always be a Q. Again, it's the exact same setup. It's just a different notation. So we can now plug in our values. All right, and you should not need a calculator for this one, but you can simply realize that Q is going to equal 1. Okay, if we compare our Q to our K, we see that Q is larger than K, therefore we're going to get a shift to the left in this equilibrium. Let's go on to B. Okay, exact same equilibrium, exact same question, different conditions. So once again, we have our QP set up for us. Okay, you can pause the video right now and plug in those numbers, please, and give this a shot before I reveal the answer. Okay, nothing crazy here. I hope you were able to do this pretty simply. Put the numbers into your Q expression, solve for Q, and then compare your Q to the K. Our K is still the exact same from the A problem. So this Q is smaller than K, therefore we're going to get a shift towards the products or to the right. One more under problem 40. Again, exact same process, exact same thinking. Go ahead, pause the video, plug in your numbers, and see what you get for the shift in C. Okay, so again, same Q, plug in the values, solve for your Q. You'll notice that the Q here in this problem is just a smidge off of our K, all right? But for our purposes and the book, if you look in the back of the book on this one, it's going to tell you that they're equivalent. If you said that Q was larger than K and that it's going to shift to the left or to the reactant side, that's perfectly fine. But this is close enough, so we're calling it equal and saying that no shift is going to occur. Okay, let's try number 52. In 52, we are given a K for this reaction up above. Okay, we have a mole of each of these gases, and we are in a 1 liter container. And we're asked to calculate the concentration of all of these things when we reach equilibrium. So a couple things to think about in this problem to start off with. Number one, we have these concentrations, or we have moles and we have a liter, sorry, and we can change them into concentrations. Okay, and the second thing is the wording of this question kind of gives it away a little bit, but it's asking us to calculate concentrations when equilibrium is reached, implying that we're currently not there. All right, so we've got to figure out how to get there, or in other words, which way is this going to shift first. Okay, so go ahead and set up a QP reaction or a QP expression for this equation. You can pause the video. Okay, so Q, again, product over reactants, nothing crazy. You should get something that looks like that. Okay, let's plug our numbers in. Much like the previous example, 1 squared over 1 times 1 is always just going to be 1. So we get a Q of 1. We compare that to the K up top. This is 100. So our Q is smaller than our K, and we're going to get a shift to the right. Now this is important first step. This is important because if we need to figure out which way this is going to shift to reach equilibrium, we can now figure out which of these concentrations, the initial concentrations, is going to go up and which is going to go down. So if we shift to the right, the reactants over here are going to go down, the product's going to go up. But in order to solve for those quantity changes, we have to set up an ice table. So what I'd like you to do is take that reaction and try to set up an ice table for yourself. Consider the shift, please, when you set up your ice table, and make the appropriate values of x in your ice table. Pause the video and give that a shot. Okay, so what we want to do is we do want to set up the reaction first, as always. Okay, we'll have ICE on the side. And in the very first line, we have our initials, initial concentrations. Again, we have 1 mole of all these gases. We have a 1 liter container. So we have 1 molar for each of these. Okay. Based on the first calculation, we solved that Q is smaller than K. So we're currently at a situation where we need to shift to the right or towards the products. Meaning, in the ice table, the things on the left are going to go down. The things on the right are going to go up. Okay. The only thing we have to be careful of here is that hopefully that you put a 2x in your ice table. And then when we reach equilibrium, we'll have the following numbers. I'm trying to get this box out of the way here. Okay, so we have the ice table filled out. The very next thing we want to do is we want to figure out, okay, well, what are these final concentrations? That's what the problem's asking us. So we do have K. We have all of these at equilibrium. Now we're going to solve for X like we've done in previous chapters. So set up the K expression, please, for this reaction. You can pause the video. Your K hopefully looks like this. Products over reactants as always, nothing crazy there. All right, and you can simply put the values in there. All right, so now here is a little tricky piece that you're allowed to do. Now, if you notice, we have this 1 plus 2x squared term on top, this 1 minus x squared term on the bottom, okay? And we have 100 on the left-hand side. So if we wanted to, we could square this term and get a x squared term, a single x term, and a numerical term up top. We could square the bottom. We would have an x squared term, a single x term, and then a numerical term on the bottom. But that would get really ugly and really messy really quickly. So instead of doing that, let's take the square root right now. If we take the square root right now, what we're going to end up with on the left-hand side is 10. What we're going to end up with on the right-hand side is 1 plus 2x divided by 1 minus x. Okay, it just simply is going to get rid of those squared terms on our in our fraction. So we get this, and that makes life much easier. Okay, we don't have to deal with any x squared terms, and now we can just simply rearrange this and solve for x. So please pause the video, catch up with the notes here, and then try to solve this for x. When you have solved for x, hopefully you got something like this. I'll show the algebra a little bit. Okay, I'm moving the bottom term and multiplying that by both sides. You get 10 minus 10x equals 1 plus 2x. Get your x's on one side and your numerical values on the other side. You solve for x and you should get 0.75. Okay, so that's our x, but this still doesn't answer the question. All right, we still are asked what the concentration of these three things are at equilibrium. But now that we know x, we can simply go back to our ice table and solve for each of these at equilibrium. So that's over here. Let me rearrange my boxes, sorry. Okay, x minus 0.75 gives you 0.25. X minus 0.75 will give you 0.25. And then 1 plus 2x will give you 2.5 molar. Okay, so a little longer problem. It involved an ice table, kind of a little bit more going on with this one. This would represent a problem that I would consider difficult as far as the chapter 13 stuff goes. Okay, number 38, another pressure-related equilibrium problem using a KP. In this one, we're asked to find a KP value both using the units of torr and the units of atmosphere, and then to compare those two. So this is a little different to start off with. What I'd like you to do before we jump in, though, is I would like you to set up that KP using the reaction given to you in this problem. So pause the video and give that a shot. Here's your K value you should have gotten. hopefully you didn't get stumped by the solid on the left-hand side and the solid on the right-hand side. We do only have two gases, so our Kp is simply going to be the hydrogen gas to the fourth power divided by the water vapor to the fourth power, and that's all we've got. Okay, now this gets a little tricky because we're given the water vapor pressure and we're given a total pressure. So something that we haven't talked about yet, but something that's very common in chemistry, is we have this law of partial pressures, okay? And that is simply going to be the total pressure is all of the partial pressures added up. Now, we only have two gases. We're given one of the gases. So we can use the total pressure they gave us, the pressure of that water vapor, and we can solve for the pressure of the hydrogen gas fairly simply. So why don't you go ahead and do that right now. You can pause the video. Okay, nothing too crazy here. I'm just going to plug in the values they gave us. You should have gotten a pressure of the hydrogen gas equal to 21.3 torr. All right, so the very first thing we can do is we do have our water vapor in a unit of torr. We have our hydrogen gas in a unit of torr. Let's plug them in to the Kp expression. It'll look like this. Okay, we have 21.3 to the fourth, 15 to the fourth. You get a Kp of 4.07. Now, if we want to try this in atmospheres, we have to convert our torrs, both the 15.0 of the water vapor and the 21.3 of the hydrogen gas, into atmospheres. The conversion for torr to atmosphere is very simple. Okay, it's just simply 1 atmosphere equals 760 torr. So, pause the video please and try to turn your 15 torr and your 21.3 torr into atmospheres now. Okay, so the calculations after you're finished, you should have gotten that the water vapor is now 0.0197 atmospheres and the hydrogen gas is 0.0280 atmospheres. Okay. To calculate for Kp with atmospheres, exact same setup, nothing different. We're still using the original Kp that we had for the first chunk of this problem, but instead we're going to plug in these new numbers. So let's go ahead and do that. Why don't you pause the video and you guys can calculate this one for me, please. Okay, you plug in your calculator and you're going to get 4.08. Now, here's the point, okay? There is a difference here, but that difference is solely due to us rounding for sig figs, okay? If you kept these values, when we change these into atmospheres, as their full values in your calculator, you would have gotten 4.07 here. So the point is that it doesn't matter which unit of pressure we use for Kp, whether we use atmospheres or torr or millimeters of mercury or some other kind of weird unit for pressure, okay? As long as they're all the exact same, as long as we don't switch units within our equilibrium expression, the Kp, or the value of that equilibrium constant, is going to be the same. Okay, now let's piggyback off that same problem and let's try this. So here are some new pressures given to you for the exact same reaction, and we're asked which ways are going to shift and which side is favored, and it doesn't matter, do the units of Q matter? So again, from the last problem, our Q is hydrogen to the fourth divided by water vapor to the fourth. The new values we have in this problem are right here. So plug that into your calculator, please. You can pause the video and give this a shot. You should get a Q of 0.441. All right, if you remember back from the previous chunk of this problem, our K value was larger than that. So if Q is smaller than K, we have to shift towards the products, or we're going to shift to the right. The very last chunk of this is asking if the units of Q matter. I think I've told you more than once, and hopefully if you haven't heard this before now, you'll remember it, but K's and Q's, equilibrium constants, and ion product quotients or mass action quotients, the Q value, they have no units whatsoever. It's one of the few things that we use in chem that actually has no label or no unit. So don't let that throw you off. This is a unitless value. All right, last one for today, number 44 from chapter 13. Little different type of problem, same kind of general concept, but a different approach to solve this one. So we're given a gas equilibrium up top. We're given a value for Kp, And in this one, we are given partial pressures for both the bromine gas and this NOBR gas, and we're asked to find what the nitrogen monoxide gas pressure is at equilibrium. Okay, so I'm going to go revert back to the previous equation that I gave you a little earlier in class, and that is that the total pressure equals the sum of all these partial pressures. So we have three gases. Okay, so our total pressure here is going to equal whatever these three all add up. Now, we don't need this in this problem, but it is important to note, okay, when we start talking about partial pressures again later in the year, this equation is going to be very, very prevalent, and I just don't want you to forget about it, so I'm going to kind of keep hammering it home as we go. But what we do need in this problem is we do need to set up a K expression. Okay, so take a second right now, pause the video, and set up the K expression for this reaction up top. Okay, you should get products over reactants as always, nothing new, pretty simple, and plug in the values that we know. We know that Kp is 109. We know that the pressure of that NOBR gas is 0.0768 atmospheres. We have to square that term. Okay, and we know that the bromine gas is 0.0159, and the unknown term is the nitrogen monoxide gas, and we have to square that. So using some algebra, I didn't show the algebra on this one. I hope you can do that by yourself. Take a second, try to solve for that unknown pressure of nitrogen monoxide right now, please. Okay, hopefully when you're all done, you ended up with a partial pressure of the 0.0583 atmospheres for that nitrogen monoxide. If you didn't quite get there, my guess is it was an algebra mistake. You do have to make sure that you keep all of your units and unknowns together in this problem to end up with this appropriate answer. All right, guys, that's all I've got. Thank you for your time. I hope everyone's doing well. I'll be back soon.